Jai Hind, dear students. I'm Dr. Preeti, and here we are back with another video for electricity chapter. In the previous video, we have seen basic terminology, electric circuits, symbol for different components of an electric circuit, electric current, potential difference, resistance, the factors affecting resistance, and we have started with combination of resistors in which we have seen the series combination. Now, in this video, we are going to start with parallel combination of resistors. Today we will be completing in this video about all the theory portion of the chapter. Fine. So let's start with that. The combination of resistances, that is the parallel combination we are going to talk about. A parallel combination of resistors is one in which the different resistors are placed in such a way that one end of them of all are connected to each other. For example, if we talk about these three resistors connected in parallel to each other, if we consider this point, so this point of this resistor is connected to the same wire as this point of another wire, another resistor. So, such a combination of resistors is known as a parallel combination. Now, in your exam, you could be having question based on proving the derivation or the formula for the parallel combination of resistors, or you can be having some numericals based on series as well as parallel combination. So, first let's have a look at the derivation, how we can derive the formula to calculate the resistance in parallel combination. So, if we have three resistors R1, R2 and R3 and they are connected in parallel to a potential source V, then what will be there? Current will be starting from this, it will come up here. Once it comes to a point where it is getting options. Now, when the current is getting options, the current will get divided. So, based on the resistance, the current will divide into some parts. The higher the resistance, the lower the amount of current will be going into that particular circuit. So, based on the resistance of different resistors, the current will be getting divided into some parts. And what will be the potential difference for all these resistors? That will be the same. R1 will also be getting V potential difference, R2 and R3 as well will be getting the same potential difference. So, in case of parallel combination, what we will write while deriving the equation, that in case of parallel combination, the total current in the circuit gets divided into parts. So, the total current is equal to sum of the individual currents. Now, according to Ohm's law, we know that according to which law? Ohm's law. We know that V is equals to IR. This implies that I is equals to V upon R. So, we'll just put the value of this. Instead of I, we can write V upon R. Instead of I1, we can write V upon R1. Why I have written V upon R1? Because potential difference in parallel combination is the same and resistance is R1. Next is V upon R2 plus V upon R3. If we take out V common, it will give you 1 upon R1 plus 1 upon R2 plus 1 upon R3. This V and V gets cancelled. So, 1 upon R is equals to 1 upon R1 plus 1 upon R2 plus 1 upon R3. So, the total resistance in parallel combination can be we can find it out by using this formula 1 upon R, that is the total resistance in parallel combination, is equals to 1 upon R1 plus 1 upon R2 plus 1 upon R3. That is for a parallel combination of resistances. By that we get that in parallel combination the resistance is not added up. In series, we have seen that the total resistance of the circuit increases too much. But in case of parallel combination, the total resistance of the circuit doesn't increase as much. For finding it out, we'll just do one numerical that will make our concepts even clear. Why at our home also we are using a parallel combination. for all our whole household electric supply, all our appliances at home like refrigerator, television, air conditioner, they are all connected to each other in parallel combination. So why we are using parallel combination? Let's see that. And we will also discuss that why we are using a voltmeter in parallel and we are using an ammeter in series. Okay, so after learning about series and parallel combination, we can get that answer also, that why ammeter in series and voltmeter in parallel. So let's do one very simple numerical based on series and parallel combination. Suppose we have three resistors, each having a resistance of say 9 ohm. And what will be the total resistance of the circuit if they are connected in series and if they are connected in parallel? Also find out the current passing through the circuit in both the combinations. If the applied potential difference is say 18 volt, okay, so total potential difference is 18 volt, the resistance of each resistor is 9 ohm. Find out how much current is passing through the circuit in both the situations and what is the total resistance of the circuit. Okay, try to do it by yourself. I'll be solving it out on the board as well. So you can pause the video, try to do it by your own. With this numerical, we will be able to draw a very important conclusion as well. So resistance of each of the resistor is 9 ohm and the potential difference is 18 volt. How many resistors we have? 3. So in series combination, the total resistance will be equal to R1 plus R2 plus R3. So that will be total making up 9 plus 9 plus 9, that is 27 ohm. So total resistance of the circuit is going to be 27 ohm. Now let's find out, if the potential difference applied is 18 volt, then how much is the current passing through the circuit? Then by Ohm's law, we know that V is equals to IR. So I is equals to V upon R, that is 18 upon 27, that is 2 by 3. 9 2s are 18, 9 3s are 27. So it's somewhere 0.6666, that could be written as 0.67 ampere. Now let's find out what about parallel combination of resistance. So the resistance in parallel combination will be equal to 1 upon R is equals to 1 upon R1, this is R in parallel combination, plus 1 upon R2 plus 1 upon R3. So it's 1 upon 9 plus 1 upon 9 plus 1 upon 9. That LCM will be 9. So it's 1 plus 1 plus 1, it makes a 3. 1 upon 3 for 1 upon R. Okay. Whenever you are doing numerical based on resistance in parallel, just remember that you write it, that is 1 upon R, that is equal to 1 upon 3, and the resistance in parallel combination is equal to 3 ohm. Reciprocate both of them. So the total resistance of this parallel combination comes out to be just 3 ohms. Whereas in series combination, the total resistance was coming out to be 27 ohm. So you can see the total resistance is even less than single resistor in parallel combination. So one benefit of using parallel combination in household circuit is that the total resistance of the combination decreases. It comes even less than the least resistance which we have used in the combination. Next, if we find out the current passing through the circuit, we know that I is equals to V upon R, and V was 18 volt and resistance is 3 ohm. So it comes out to be 6 ampere current that is flowing through the circuit. So a lot of current will be flowing through the circuit. 6 ampere current will be flowing through the circuit in parallel combination. Whereas in series it was just coming to be 0.66. So you can see that great difference. That is why we prefer parallel combination in household circuit. One more benefit of that is that in case of series combination, when two or three or any number of resistors are connected to each other end to end to a potential source, then if any of the resistors gets broken off, means if any one of the circuit is turned off, or we switch off any one of the appliances, these are three appliances and we are turning off any of the three appliances, then the whole circuit will be broken off and the current will not be flowing. So in order to keep our AC on at night during summers, we have to keep on all the lights of the house, the refrigerator, the washing machine, everything needs to be turned on only. That is not practically possible. So that is why we don't use series combination at home, but rather use parallel combination. Then why we are using series combination Diwali lights, the fairy lights that we are using at Diwali decoration? Because we have to connect so many bulbs one after the other, and connecting so many bulbs within parallel combination will require a long wire for each and every bulb. So that is not very practical now. So for that reason, in Diwali lights, when we have to use hundreds of bulbs end to end, it's easier for us to connect them in series and just put some of the like series combination and some of them in parallel combination. So we use a system both series as well as parallel for our total Diwali lightings. Okay, that is why you must have observed that during Diwali lights, if one the bulb is dead and it's not working, then the whole circuit needs to be checked and you have to find out which one is a dead bulb. So you have to remove that from the circuit and rejoin the circuit so that the entire series will be working again. Okay, so that's all about the series and parallel combination of resistors and one numerical based on that. Let's practice one more very important numerical based on resistors only. That suppose we have a wire whose resistance is you can take any example whose resistance is suppose 4 ohm. Okay, now you the length of the wire is decreased to half and its area becomes 2 times of the original area. Okay, new length is half of the original length and new area is twice the area of the original wire, and the second wire is also made up of the same material. Then what will be the resistance of this new wire? That you have to find out. Calculate that, try to find it out by yourself, and then I'll be solving it on the board. So we all know that this R is equals to 4 is solved by the formula R is equals to rho L upon A. That is the formula to calculate resistance. Now when we want to calculate this R dash is equals to rho L dash upon A dash. Now we'll just put the values. So we'll get R dash is equals to rho L dash. What is the value of L dash? That is L upon 2. Original length divided by 2. And new area A dash is equals to 2A. So we get rho L upon 2 times is 4A. Now the value of rho L upon A is already given in the question, it's 4 ohm. So instead of rho L upon A, we can use 4 and here we have divided by 4. So the new resistance of this wire comes out to be 1 ohm. Okay. Likewise, we can find out the resistance of any new wire, whatever conditions are given in the question accordingly. So that was about just 2 numericals we have practiced right now, but we are going to practice a lot of numericals in the next video. So let's come to the next point, that is about heating effect of electric current. Again, a very important topic. Heating effect of electric current. So When current is passing through a conductor, then the electrons in the wire are continuously colliding with each other. So that produces some, due to that collision, some heat is produced. If this collision is more, then the heat generated is also more, and that results in the heating of the devices. You must have observed when you turn on the fan, and if you try to touch the fan, the motor area, after some time you feel that it is getting something warm because of heating effect of electric current. Apart from that also, if you touch an electric bulb, that you can find that it's hot to touch. So that is also because of heating effect of electric current. Apart from that, the electric iron, geyser, immersion rod, these are all the practical applications of heating effect of electric current that are useful for us. Okay, so let's see how much heat will be produced and how we can calculate the heat produced in a conductor. But before that, just recall something that we have seen yesterday. We have seen that potential difference is the work done to carry a unit charge from one place to another. So we can also write W is equals to V into Q. Now remember, this work and energy are interconvertible. So if you are asked to calculate the electrical energy, and if in the question you are given the potential difference and the charges, then just multiply both of them and you will get the heat produced in the conductor. Okay, so if we take work done, or if you are asked to calculate the electrical energy, then also the formula is the same. If you are asked to calculate the heat generated in the circuit, then also you can use the same formula, because heat, work, and electrical energy, they are all interconvertible. That is why all have the same SI unit, that is joules. So we have W is equals to V into Q. Okay. Now we all know that if using this formula we have to calculate how much heat is generated, and if Q is not given, then we can replace it. And we want to, if we want to replace both these terms, let's see how we can replace that according to Ohm's law. What is V equals to? V is equals to IR. So instead of V, I can write IR. And what is Q? If you remember, electric current is the charges flowing through a conductor per unit time. So I can write Q is equals to I into T by cross multiplying that. So Q equals to IT, and we get I square RT. So work done is also equal to I square RT. Suppose whatever work is done in transferring these charges, that is all converted to heat. Then heat generated in the wire will also be equal to I square RT. And this is the formula for heating effect of electric current, which is also known as Joule's law of heating. Joule's law of heating is I square RT. If you are asked to define Joule's law of heating, this we have to write the same formula in words. How will write that? According to Joule's law of heating, the heat generated in a conductor is directly proportional to the square of the current. Then heat generated in a conductor is directly proportional to the resistance of the circuit, and heat generated is directly proportional to the time duration for which current is flowing in that circuit. So that is the Joule's law of heating. That can come as a 2 marks question. So we can define very easily the Joule's law of heating. Okay. Based on the same calculations, we can even find out the formula for electric power. Let's find it out. So we know that what is power in general. I'm just erasing this one and I'll be using the same board. So we have got two formula today. W is equals to V into Q, remember that, and H is equals to I squared RT. That also is important. Okay. In fact, you can also write this as work done is equals to V I T. In case time is given, current is given, and potential difference is given, then you can use this formula also. So work or energy or heat energy, whatever is asked in the question, that is also equal to potential difference multiplied by current multiplied by time duration. That will also give you that. Okay, so H is equal, W is equals to V into Q. W is equals to VIT also, and H is equals to I square RT also. These three formula will be there. Now, in general, you all know that power is the work done per unit time. Power is always the work done per unit time. So, just replacing the value instead of work done, what I can write is V into Q and upon T is there. But Q upon T is equal to, remember, I. That is equal to I, current. Current is the charges flowing through a conductor per unit time. So, power is equals to V into I, and we get the formula that P equals to VI. Or you can remember that power is very important in life in current chapter. So, power is very important. And if you are asked to find out to define 1 watt, what is the SI unit of power? So, what is 1 watt? How will you define that? 1 watt is the power generated when 1 volt potential difference is applied and a current of 1 ampere passes through the circuit. Then the power is said to be 1 watt. Okay. So, if you are asked to define anything, just use that formula and you can easily define that. Okay. Now, instead of VI, we can use other formulas also. For example, V is equals to IR in case potential difference is not given and only current and resistance is given. So, we can use the formula P equals to VI and V is equals to IR. So, we get the formula I square R. Instead of I, if suppose V is given and R is given but I is not given, we can replace I also, that is V into I is equals to V upon R. So, we get the formula V square upon R. So, for power we have three formula, P equals to VI, P equals to I square R, P equals to V square upon R. Depending what values are given in the question, we can apply the formula. Okay, you can just take a screenshot of all these formula. These will be very useful for you all in your exams for solving out the numericals. So, just take a screenshot of these. I hope you have taken a screenshot. So, we are left with the last topic, that is practical applications of this heating effect of electric current. In the starting only we have discussed that this heating effect of electric current is very useful in heating devices like electric iron, electric geyser, immersion rod. All these are based on Joule's law of heating only, because in them heat energy is converted into the electrical energy is converted into heat energy. The second device which is based on heating effect of electric current, that is fuse wire. Fuse wire is also based on the heating effect of electric current only. What is a fuse wire? It is a safety device used in our household circuits. So, it's a safety device used in our household circuits. For example, if we have an electric iron, and this is a wire coming out of that. So, if there is some potential hike, sometimes the potential difference is different. Sometimes you have voltage fluctuation at home. So, if there is a voltage hike, higher potential difference is there. So, then what will happen? If the potential difference is increased, then the current flowing through the circuit also increases. And when the current flowing through the circuit increases, what could happen is, because of excessive heating inside the electric iron, the wires made up of copper that are there in the electric circuit, that can melt away. But we don't want that. We want to save our electric iron. So, in all important devices, we have a fuse wire next to it. Here, before the wire enters into our electric circuit carrying the current, a fuse wire is placed in series to that. Why in series? Because in series combination, the current through the circuit remains the same. So, here we place a fuse wire, and this what will happen when the current whenever there is any potential hike, if the potential difference is too much, then what will happen? The fuse wire is having a peculiar melting point. It could be, this fuse wire could be made up of copper, aluminum, depending how much heating we want it, how much we want its melting point to be. So it allows a peculiar amount of current to pass through it. For example, if it allows 5 ampere current to pass through it, and if the current coming through the circuit increases to 6 ampere, then because of that increased current, according to heating effect of electric current, we know that I square RT is their formula. So if more current is there, then the heating will also be more, and because of excessive heating, this fuse wire is going to melt away, and that will break the circuit, and we want that the circuit should be broken. Otherwise all the wires inside the electric iron could be damaged because of that. So we don't want that. We just want that the fuse wire could melt at that high temperature, and our device will be saved. A similar fuse wire is also there in our electric main supply also. That is a precautionary device that is there in our appliances, that is a safety measure for our electrical devices to keep them protected. Okay, in exam sometimes you can have a question, what are the two safety devices used in household electric circuits? So what are the two safety devices? One of them is fuse, the other one we are going to see in magnetic effect of electric current, that is earth wire. We have already seen that actually. So that is earthing. Earthing and fuse wire are the two devices that are there in household circuits that are acting as a precautionary devices to protect our devices. So that is the second practical application of Joule's law of heating, the fuse wire. Third one is electric bulb. In electric bulb, we have a filament, and that filament is almost exclusively made up of tungsten. The tungsten is very special because it doesn't oxidizes very easily, it doesn't melt at a very high temperature, and second property is that this tungsten wire has a peculiar property that it, at when heated at a very high temperature, it starts emitting out light. So because of that, we are using this tungsten wire in electric bulbs, and that is another practical application of heating effect of electric current. So there are three applications. One is electric iron, electric geyser. These are all based on heating effect. Second is electric fuse, and the third is electric bulb. Now we are left with the last topic of our chapter. Based on that also we have some numericals in our exams, that is electrical energy. Electrical energy that we are using at home, and for that we need to pay to the government, because every month you are paying for the electricity bill at your home. So what are paying for? We are paying for the electrical energy that we are consuming. Okay, so let's talk about that how much we need to pay and how we are paying that, how it is all calculated. Okay, so we know that in power is the work done per unit time, or we can also they say that in terms of work and energy are interconvertible. So I can say energy upon time is power, or I can say energy is equals to power multiplied by time. When we talk about electrical energy is equal to power multiplied by time. But when we are talking about household circuits, when we are talking about electricity bill that will be there at your home, then we cannot calculate these values in their SI unit. For example, if you are calculating the time in seconds, which is the SI unit, then the electricity bill will be too lengthy to calculate. Just imagine you have to multiply the number of hours you have used your fans during the whole month and multiply it with it and convert the values in seconds. So that's useless. For that reason, we use commercial unit of electrical energy. For calculating the bills, we use the commercial unit of electrical energy, and in that commercial unit of electrical energy, this power is taken in kilowatt and time is taken in hours. So electrical energy is equals to power in kilowatt and time in hours. So we just simply say it as kilowatt hour. So what is the unit? What is the commercial unit of electrical energy? That is kilowatt hour. And what is the SI unit of electrical energy? That is the same as energy. That is the same as work. That is joules. Okay. So the commercial unit of electrical energy is kilowatt hour and its SI unit is joules only. Let's do one numerical based on that. I'm giving you a question. Just note it down. Try to solve it by yourself and then we'll be solving together. So, calculate the bill, calculate the electricity bill for using two bulbs of 100 watt each for 6 hours daily for 30 days at the rate of rupees 8 per unit. Calculate the electricity bill for using two bulbs of 100 watt each for 6 hours daily for 30 days at the rate of rupees 8 per unit. Try to solve it out by yourself and then you can see the solution. So we know that when you have to do this numerical, most of the students land up with the correct answer. But usually forget to write the correct formula and just land up with the correct answer. So you have to learn to get the correct answer with the correct method as well. So let's see how you need to solve it out. So when we have to calculate the electricity bill, first we'll calculate the electrical energy consumed. So write electrical energy consumed is equals to power, that should be in kilowatt, multiplied by time, that should be in hours. So we get power is 2 into 100, but this is in watt, so we have to convert it into kilowatt. So divided by 1000 multiplied by time. Time is 6 hours and it's not just used for a day, it is for 30 days. So total time is 6 into 30. Now we'll solve it out and we'll get 18 to 36 units. So how many units we have consumed? That is 36. At your home also, when your electricity bill comes, sometimes we talk about that how many units are there in the electricity bill this time. So that is with the units is equal to kilowatt hour. 1 unit is equals to kilowatt hour. So we can write in terms of units or we can write 36 kilowatt hour. 1 kilowatt hour is equals to 1 unit. Now we have to calculate the bill. So we'll write cost of 1 unit. Cost of 1 unit is given in the question as rupees 8. So what will be the cost of 36 units? We'll calculate that. So it's 36 times 8 and it comes out to be 288. It comes out to be rupees 288. So that much amount we have to pay for using two bulbs of 100 watt each for 6 hours for 30 days at the rate of rupees 8. So by this way we have came to the end of the chapter. But in the middle we have discussed about ammeter and voltmeter, and I told you that ammeter is connected in series. Why we are connected in a series? That's all not given in the NCERT book. That is something extra that I am telling you. Ammeter is connected in series because in series only the current remains same and ammeter has to measure the current. So it has to be the same as in this total circuit. A voltmeter is connected in parallel because in parallel combination only we have seen that the potential difference remains the same. So for that reason we are connecting a voltmeter in parallel. One more extra thing, that how we keep the resistance of an ammeter. A resistance of an ammeter is kept in such a way that's very low so that it doesn't increase the total resistance of our circuit, and that of a voltmeter is kept very high. The resistance of a voltmeter is kept very high so that maximum current flows through a main circuit only and not through the voltmeter. Okay, so by that we have completed with all the theory portion and some numericals of the chapter electricity. In the next video we will discuss and we will practice many numericals from the chapter. Okay, so that's all for today. Good day everyone.